Today we will see the force acting on a current carrying conductor placed in a uniform magnetic field. So when a current carrying conductor is placed in a uniform field, what happens is, yesterday we have seen in the previous class that when a charged particle is moving in a uniform electric field with a velocity v, then it is exerted upon by a force. So as the conductor has so many free electrons and they are moving with a drift velocity, as we know, when current is set up, all the electrons are drifted, and this is the conventional current which we have shown. So when the electrons are in motion, definitely a force will be acted. That force is F dash. So the net force acting on all the electrons will exert a force on the conductor, and thus we want to find the relation for the force acting on a current carrying conductor. Okay, so I have taken a conductor of length L, current is I, area of cross section is A, magnetic field is in the plane of the paper. In this plane of paper, the magnetic field is there downwards, right? So this cross means the field is in the paper. So magnetic field is vertical downwards. Current is I, area of cross section is A of the conductor, length is L. Now in this case, again we'll use the Fleming's left hand rule to find the direction of the force. So the forefinger, the middle finger and thumb, they are arranged such that they are mutually, or they are stretched in such a way that they are mutually perpendicular to each other. Then the forefinger point in the direction of magnetic field, the middle finger point in the direction of the current, then the thumb, stretched thumb, gives the direction of the force acting on the conductor. Okay, so the same we have seen, only instead of current it was the velocity in the case of the charge conductor moving in uniform magnetic field. So let us now derive the relation. So as I told, the length is L, cross section area is A. So let us consider on one of the electron, the force F dash is given by Q into V cross B. This is the Lorentz force acting on one electron. So F dash is equals to Q into the velocity with which electron is moving is the drift velocity into B into sine theta. Okay, so F dash is equals to QVD B sine theta. Now this is the force exerted on one electron. So I want to find the total force acting on the number of electrons which are present in this conductor. So let capital N be the number of electrons present in the conductor. Okay, so capital N can be given as small n. I hope you know small n is number of electrons per unit volume into area into length. So this is volume into n. So this is the number of electrons. So the net force or total force is equals to n into F dash. So this will come out to be n into QVD into B into sine theta. Correct? So what is n? N is equals to capital N equals to small n AL VD into, now the charge I will substitute as E, it is the electronic charge, into B sine theta. So I know NEA into VD is current I. What is remaining here? NL B sine theta. Yes, so the force F comes out to be IBL sine theta. So as the force is a vector quantity, I can write the force in vector form as vector F is equals to I into L cross B. Okay, so here we will discuss the cases immediately so that we will be able to get the idea about it. So if case 1, if theta is equals to 0, F is equals to IBL into sine 0, and sine 0 is 0, so force is equal to 0. Correct? And second case, if theta is equals to 90, F is equals to IBL sine 90. Sine 90 is 1, so it is BIL. This is the maximum force acting on it. Okay, I hope you understood this much. That is the force. So this is the expression for the force acting on a current carrying conductor placed in uniform magnetic field.